Hush!
We're Group 7. Our project was the Cool Train. It's a train that you can control from the hallway outside Durham 375. Basically, the only constraints on the project were that it had to be fun and intuitive, it had to attract people, and we couldn't have anything outside the room in the hallway because we can't trust anybody to not steal things or break them. It's also supposed to be fun without anybody playing with it. It has to attract people and be interesting.
How does that work?
Well, you see, our timers are interrupt-based, so we have a timer event loop, and that generates periodic interrupts. At each timer expiration, we start an ADC acquisition. When the ADC acquisition completes, a conversion begins, and the conversion generates an interrupt when it's complete. When it's done, we get an interrupt, and then we can read the ADC value, convert that to a message, and place that into a queue.
Alright, but how does that actually move the trains?
Well, you see, once the message is placed in the queue, it needs to be sent over I2C. You are familiar with I2C.
Oh, right. I forgot completely about that. That's right. The Spartan board itself generates an interrupt on the PIC, which will begin an I2C response.
Really?
That will send back the proper message to the Spartan board so that it will be able to process the information as needed and do whatever it needs to do. For our project, the first thing the user does is they use their hand to activate one of the cups. The cups will activate here, and they will go into one of the ADC sensors on the PIC. On the ADC sensor on the PIC, it will put it into a message queue that will then be transferred over I2C over to the Spartan board. The Spartan board will interpret the messages and send a specific command to the LocoNet PIC, which will push it out over to LocoNet and move the train specifically. We have a few messages here. We have the speed up, which speeds up the train, slow down, which slows down the trains and eventually stops the train, and we have two switches that can be changed on and off to represent the front switch closer here and the back switch, which is on the far side of the track.
On the track, it can be observed that the directional sensors dictate which path the train will take. We consider the Spartan board to be the central hub to make decisions and handle control logic. The individual PICs are single-purpose slaves that control only one component of the project. For instance, we have one PIC that controls the Hall effect magnetic sensors and collect analog voltages that way. We have another PIC that manages the UI sensor messages from the window, and another PIC that controls LocoNet messages. As a result, the Spartan board is the I2C master and is responsible for pulling peripheral devices for data. As you can see here, I2C messages are being sent out from the Spartan board over I2C, and they're being received over here on the window PIC. The LEDs on the PIC are set when a message is received and cleared when the response is sent.
In order to make the project more interesting, the plan was to run two trains on the track simultaneously. One train, indicated by an LED, would be controlled by the user, whereas the other would be automatically routed. When the user applies input to the outside window sensors, the SCE's train controller state machine would determine if the new input would put the trains on a collision course. If so, the train would be automatically rerouted to avoid collisions. Otherwise, the input would be denied.
An important part about our photoresistive sensors is that they look for differential changes in voltage over time. So, if the lights are on inside the cell, they actually change the amount of light that the photoresistive sensors see. And as you can see now, they're fully calibrated and work properly in full light. If the lights turn off, however, they are looking for differential changes in time, so that no spurious messages were sent, and the sensors still work and the train still responds to messages. The photoresistive sensors are simply photoresistors placed inside a cup. They are very noisy, and they have to have a sophisticated debouncing algorithm in order to effectively only get one message when the button is pressed. This graphic describes how the debouncing procedure works. We have this noisy analog signal that goes into the ADC on the PIC. The ADC will sample each sensor over time
and come up with a listing of discrete points over time that show how the voltage has changed. If that change is a precipitous voltage change over time and ends below a certain threshold, then the sensor is said to be on. The inverse is also true for turning off, except that the algorithm looks for a change upward. Once the sensors are debounced, then they can be placed into the queue. 8 Hall-effect train sensors were soldered and placed right before turnouts around the track. These sensors act as a 1-bit latch and are set to 1 by the south pole of a magnet and are cleared by a north pole. We mounted magnets on the train so as they pass by, they would pull the sensor line high when the train's south pole goes by and low when the north pole goes by. In order to send textual messages to the user, we built a persistence of vision wand that consists of a string of 8 LEDs that will send a textual message by turning the LEDs on and off very quickly as the device rotates. The initial plan was to send a message over I2C that would ultimately be coded over infrared to this chip here that would be routed down the sensor line and would send the type of message to be displayed on the wand. Due to time constraints, we were unable to actually implement the IR transmitter, although this receiver module works for the default welcome message.
This is the fab board. It has 4 different components supporting the main PIC chip. It has 6 AD circuits in here that work as mini voltage divider circuits that will control the input from the sensors so that they can be read more easily on the channels. It has a voltage regulator which will step down any of the different voltages coming in from either the I2C circuit or the PIC kit. It has the PIC kit 2 I/O, which is just a little bit of wiring, nothing too special there. It also has the I2C bus going on here, and it has an extra little header for different UART communications that we would have used for the LED wand if it was implemented.
This right here is the Locanet PIC. It connects to the Locanet board and it sends Locanet commands to the DCS50 via UART. It's on this I2C bus here, and the Spartan board sends out I2C messages, which are basically commands for the trains, to the Locanet board. It translates them into Locanet messages and then sends them out via UART to the DCS50, and then it converts those to DCC commands, which actually move the trains. This board also has the capability of sending back an error message to the Spartan board if something goes wrong with the trains. Say the acquisition fails and the train's already in use, it can set an error bit and send a message back to the Spartan board to notify.
The board here is the master of the system, which in turn holds many of the threads that are responsible for the system acting as it should. We have a controller thread which manages polling with timer interrupts. We have an I2C thread which manages sending and receiving messages between different PICs. We have the processing thread which handles the messages that have been received and passes them along to the state machine after parsing the information. We also have a train control thread which manages the state machine that automates the train system. When the error handling includes when a PIC is disconnected, the message queues between threads are tied, and a PIC disconnected error is displayed.
Had we had more time, there were several issues with the sensors that we would like to address. For one, the Hall effect PIC sensor demonstrated an issue where it would hold the I2C clock low after a seemingly arbitrary number of successful bus transactions. This number was in the ballpark of 3 to 5. For this reason, we've removed it from the project for the purpose of the demonstration. Without that PIC on the network, the system ran for approximately 2.5 hours, functioning properly. As far as the photoresistive sensors are concerned, we could have possibly replaced it with something along the lines of ultrasonic that would allow for operation in lower levels of light. As demonstrated previously, the photoresistive sensors did work when the lights in the lab were turned off, but if the lights in the hallway are turned off, then they will simply report an error message.
There were several ways we could have improved the I2C communications. The first thing we could have done is we could have enabled some kind of timers to check and to periodically see whether the I2C communications failed. We we could have then reset the circuits from within and kept everything going. The other possibility is we could have prevented the entire circuit from just consistently polling all the picks to see what new information they have. We could have handed along the master through the multi-master mode and have that send the necessary information places.
Additionally, the LED one could have been more fully integrated into the system. For one, the Atmel microprocessor used on the LED had a very limited amount of memory and couldn't store more than 2 messages. To address this, we could have added an external non-volatile memory, or ROM, to the Atmel and interface that with the microprocessor to provide more storage. Additionally, a PIC circuit could have been built to transmit a 38 kHz modulated IR signal to the LED to respond from feedback sent from the Spartan board. The device could have also been mounted in a more permanent manner than taped to a box fan, and the speed of the box fan could have been made to make the text more easier to read. We think the best approach to this would be through a customized apparatus based on the DC motor and addressable via I2C.
Ideally, if we had more time, we would have liked to give the users more things to do with the trains, such as a little game where, say, they would race another train around the tracks, or possibly a game where they would have to run around the tracks trying to turn off these little light sensors that we would set up around the track.